This is our first Turing-Roche Knowledge Share series event, and the aim of these events are to showcase research the partnership is producing and to bring together members of the Turing-Roche networks and beyond to network, hear different perspectives, and ultimately build new connections. We're starting off with a monthly event, and we'll be experimenting with the format over the next few events. If you're interested in getting involved, then please connect with us via the Slack. So just to get started today with some slides, I'll just share my screen. I hope you can see that okay. So yeah, as mentioned, I'm Vicky Hellon. I'm a community manager for the partnership. And today we're joined by Robin and Chris. So Dr. Robin Mitra is a senior lecturer in mathematics at Cardiff University. And he also is part of the partnership as a research lead. And we're also joined by Dr. Chris Harbron, who's also part of the core partnership team and is expert statistical scientist and advanced analytics lead at Roche. And they're both going to be talking to us about missing data. Before we hear from them, I'm just going to give a very quick overview of the partnership. The clue is in the name of the partnership. It's between the Alan Turing Institute and Roche. I'm sure most of you will be familiar with at least one of these organizations, but just a quick overview if not. So the Alan Turing Institute was established in 2015 as the National Institute for Data Science and AI. We're made up of a network of 13 universities and do broad research in a huge kind of range of disciplines. So this partnership sits under our Health and Medical Sciences program. Roche, for many of you will be familiar, is a leading healthcare company with a long-term interest in personalized healthcare. And they also have established an advanced analytics network. We initially collaborated as two organizations through a Turing-style hackathon called a data study group. And then we took part in a 12-week research project before formally launching our 5-year partnership in June 2021. And our kind of guiding star, our North Star we refer to for the partnership that we want to achieve over the 5 years is enabling the generation of insights to better understand patient and disease heterogeneity. And it's relevant to clinical outcomes at an unprecedented level of precision in order to improve clinical care. So as you can see, there's a lot of different research areas and activities we could kind of explore within this North Star. And what's also not reflected here is the kind of connections and collaborations we want to build. So it's critical for us to be running events like these to kind of get the wider community involved. And the first research theme we focused on as a partnership has been what we're deeming structured missingness, hence today's topic. There's a very simplified definition there that Chris will be expanding on later. So we actually ran 3 collaborative workshops in this area at the end of last year, exploring ideas with a mix of 40 researchers. And there's a full report about this on the website if you'd like to read more. We then ran an associated funding call to fund some of the ideas that came out of the workshop, and we'll be announcing these successful projects soon. And we'll be very much encouraging them to work in the open and get input from the community. So please do keep your eyes peeled on this. And with that, I'm going to hand over to Robin.
Sorry, just unmute myself. Thank you. Okay. Sorry. Am I okay? That's something popped up on my screen. Okay. Share my screen.
That looks good, Robin.
Cool. Okay, great. So it's displaying okay, Vicky?
Yeah, all good.
Great. Thank you very much. Thank you, Vicky, for the great introduction. So I'm going to be first giving a brief review of some of the fundamental concepts in missing data, as well as then moving on to an empirical application where we'll be looking at a study on survival times following undergoing an organ transplant. Okay, so I'll first give, as I say, a brief overview to the area of missing data, and then I'll go on to perhaps one of the most appealing ways to deal with missing data and give a brief explanation of what this is, called multiple imputation. We'll then look at an application relevant to to dealing with problems of missing data on the survival study post-organ transplant. And then I'll end with a few concluding remarks. So, okay, so the nice thing about missing data is it's quite a transparent problem, so it doesn't need a lot of explanation as to what it is. It's data that you would have liked to have had to use in some analysis, but for whatever reason, that data didn't come through. So that data isn't there for the analyst. And it's a really common unavoidable problem in many fields. So anyone that works with real data will unfortunately probably encounter it in some form at some point. And the key point is that something has to be done, right? Because if you have missing values there, it's going to complicate typical analyses. You've got holes in the data that have to somehow be rectified. And so, you know, this is going to complicate analyses analysts wish to perform. So what's the sort of simplest things we can do? Well, many things, the simplest thing is probably something that people do without perhaps even realizing they do it, which is called complete case analysis. It's the simplest method where you essentially throw away any unit or row in the data that has missing values. And so you just essentially just restrict your analysis to the subsample of fully observed rows or units in your data set, and then you don't have to deal with the missing data anymore. So this is sort of forming a class of what we call ad hoc methods to deal with missing data, but they can severely compromise the validity of any analyses performed. More on that in a little bit. So before we go into sort of how to deal with missing data, it's worth sort of reviewing some of the fundamentals, and in particular, we call this missing data mechanisms. So I like to sort of describe this by saying not all missing data are the same. And so we need to consider the process or mechanism that causes the data to be missing, and which is what we call missing data mechanisms. And this can be broken down into three broad categories. So the first is called missing completely at random, and this is where the missing values arise independently of any variables of interest. Then you come to missing at random, where the missing data mechanism depends on some variables of interest, but these are all crucially going to be observed. And then you get to not missing at random, where again, the mechanism depends on variables of interest, but now some of them may be unobserved or missing, which, as perhaps apparent, will complicate the problem. Okay, so just a little illustration to just sort of highlight the differences. Suppose we're conducting a survey of people's income, and we see that some of the income values end up being missing. So there are different reasons or causes for why these values could be missing, right? So if we suspect that people with higher incomes, for example, are less likely to report their income, then that's basically saying that the chance of an income value being missing depends on the income value itself. That's a classic example of not missing at random. So that's sort of the most challenging scenario we have. If we think that people's job category instead is what determines whether missing data arises, so it's not the income value itself, but someone's job, which is, let's say, observed because we could maybe have that observed in the data set, or we can get that from some external source of information, then we have missing at random. And if missing income values arise purely as a random sample within the survey, say, so there's no really rhyme or reason to who reports their income and who doesn't, then we have missing completely at random. Now, it's worth noting that sometimes the distinction between not missing at random and missing at random is sometimes subtle, because it could be that a person's job category could be also quite highly correlated with income. So some job categories might be higher earning than others. So you might still have, under missing at random, people with higher incomes not reporting their income, but it's the job category that's driving whether someone is more likely to report their income or not. And so the distinction can be subtle, and it essentially boils down to what we call conditional independence arguments. Now, in terms of practicalities, if you have not missing at random, there's not much you can do. It's a very challenging setting to be in. So often in the literature, it's normal to sort of assume you have missing completely at random or missing at random, because then you have methods that can work well to deal with the missing data. In particular, if you have missing completely at random, then complete case analysis would result in unbiased estimates. So with respect to bias, at least, you can do a complete case analysis, and that's going to be relevant later. But even if that's the case, it's not necessarily the best thing to do because it could end up being very inefficient. So just to give you an illustration, suppose we have a data set with 5 variables, body mass index, race, gender, age, and some renal disease status, say. And the question marks are denoting missing observations. If you wanted to do a complete case analysis here, well, what's the problem? Well, although the amount of missing data doesn't seem too bad, the way it's spread out sort of in this way means you end up with only 2 fully observed rows here. So you're throwing away a lot of data. Now, obviously, this is a fictitious example. You would have a lot more rows of data, but you would also probably have a lot more variables as well. So the loss of data when you do a complete case analysis is often non-trivial. So what we want to do basically is address the missing data problem appropriately, but it'd be nice if you could keep some of the simplicity or the sort of ease the burden in some senses on the analysts as like complete case analysis does. So this is what multiple imputation has been motivated by, to try and deal with the missing data in a principled way, but not significantly increasing the burden on analysts. Okay, so what is multiple imputation? So multiple imputation treats the missing data problem and the analysis of the data in 2 distinct stages. So firstly, you have an imputer. That's maybe a trained statistical modeler that's well-versed in dealing with missing data problems, and they deal with the missing data. So they do this by forming a model for the complete data, and then they impute the missing data conditional on the observed data. So from this like full conditional distribution, that if you're a Bayesian, you would call this a posterior predictive distribution. And they do this multiple times, m times, say, to generate m multiply imputed data sets. So each of these data sets now has the missing values filled in or imputed using this model to impute the missing values. And then you release those imputed data sets to analysts who can treat each imputed data set as if it were the original fully observed data. And crucially, each of these data sets is now fully observed, so they can apply their standard statistical analysis that they were going to have done originally if the data was fully observed. So they can just proceed in this essentially the same way as they would have done before. So in this way, the burden of dealing with the missing data largely falls on the imputer and not the analyst. So that's a sort of a nice appealing feature of multiple imputation. Just to give a simple illustration, hopefully it's clear, but if not, hopefully this will help. So let's say we have an observed data set with just 2 variables, x1 and x2. There's some question marks in x2 denoting missing observations. The imputer will form a model that relates x1 to x2. And using the conditional predictive distribution from that model, they'll impute the missing values. Here we've done it 3 times to generate 3 multiply imputed data sets. Okay, so the one additional complication for the analyst is that they now have multiple data sets to deal with rather than 1, but that isn't as bad as you might think. So essentially, we assume that the analyst wants to infer some quantity from a population, say. This could be a mean of a variable or, say, a regression coefficient from some regression model fitted to the data. And so in order to do that, they would take each imputed data set, and as before, you just treat it as if it were the original fully observed data set. So pretend that's the original fully observed data set, and then apply your statistical procedure that you're always going to apply on the observed data and obtain your point and variance estimates. So you would have had to have done this on the original data if it was fully observed, so there's no real difference here. You're just obtaining a point and variance estimate in the usual way, Q and U. The only difference is that you're doing this multiple times on each of these m imputed data sets. So you got m sets of point estimates and variance estimates. So, but the combining rules are relatively simple, and they're grounded in theory to ensure they're principled. You essentially take the mean of your point estimates, Q bar, and you take your mean of your variance estimates, your m variance estimates, U bar. And so those are quite intuitive, I think, probably think of doing those things anyways. And the one thing that is perhaps less intuitive is this quantity here, B, which is the sample variance of your point estimates. So your sample variance of your Q, of your Qs, your point estimates. So the reason that you do this is the following. So if you want to get a point estimate that just to summarize, a 1-number summary for your quantity of interest, that's your Q bar, your mean of your point estimates. Fairly intuitive, I think that's what you would do. And the reason you do this B is for your variance, you don't just use your U bar, your average of your variance estimates. It's U bar plus 1 over m times by B. So this B here is the additional term that you need. And that, if you think about it, is adding an additional piece of uncertainty into your inferences, because you always had this missing data. You haven't got rid of it. So it's important that you adequately inflate your variances and adequately incorporate that uncertainty into your inferences. And this is what's allowing this to happen here. So now you've got a point estimate and you've got a variance estimate. You can now make inferences in a very similar way to before. For example, if you want to create a confidence interval, you can do that on a t distribution. The degree of freedom is a little bit fiddly, but it is just a function of your u and your b. Standard routines in software packages can perform these calculations now. So the mice package in R is a very popular one that people use that can perform these sort of combining rules and create inferences as required. Okay, so now I'll move on to the survival study to give some illustrations of this and why it's important to think about. So, so this was a study that examined survival times of patients after undergoing a kidney transplant. So patients in the study underwent a transplant between 2001 and 2008, and then they were followed up after this to see how long they survived. Now, obviously, something of interest would be, are there any relevant background or covariates that are associated with survival? So they collected data on a whole range of variables: demographic, health, socioeconomic variables. So, for example, gender for both recipient and donor, I should say, gender, body mass index, BMI, ACON index as a measure of social deprivation. And an analysis of interest was to determine the effect of these variables on survival. Before we began, turned out there was a special type of what we called a missing data by design problem that arose here. So up until 2003, recipient BMI wasn't recorded, simply because it wasn't deemed to be something that was needed to be recorded or relevant. And in subsequent years, it was still missing for a large proportion of patients because some transplant centers switched more earlier than others to start recording this information. So in that data set we have about approximately 64% of patients that were missing in this variable. So given how the missing data arose, there's no real sort of informative sort of process there. We don't think that the people that had a missing recipient BMI were in any sense qualitatively different to those that did have it observed. It was just that it was not realized to be important at the time that they were undergoing the entering the study. Complete case analysis should result in unbiased estimates. So that's one reason that people would think about doing a complete case analysis here, right? This gives unbiased results. And also when we talk to sort of practitioners in the area, there was also some skepticism we encountered about imputing such a large amount of data, because imputing is sometimes seen to be making data up, right? So so people were sort of nervous about, you know, drawing inferences with such a large amount of imputed data when we're doing the analysis. But it's worth noting that complete case analysis isn't a free lunch, right? Come back to that example illustration earlier. In this situation, if you do a complete case analysis, you only end up with about 27.6% of the data present. So you're losing a lot of data that could have been potentially useful in making the inferences. Okay, so we wanted to just see whether multiple imputation might have some advantages here. So we compare it to complete case analysis. I won't go into some of the technical details because of time, but the analysis model we fitted to allow us to determine relationships between the different covariate variables and survival is what's called a Cox proportional hazards regression model. I think many people here might be familiar with it already, but it's essentially a regression model that allows us to look at what the effects of the different variables are on survival. We know that not all the variables will be significantly associated with survival. So we used a really neat method by Wood et al. That allow us to perform a stepwise regression using multiply imputed data to find a subset of variables that are significant on survival. And on that subset of variables, we compare point and interval estimates obtained from multiple imputation and complete cases. We did the imputation using the mice package in R. Again, won't go through all the details, but it essentially imputes the missing values using a sequence of full conditional regression models that are fit to the data. And it's a very convenient package that can be easily used in R. I'm not presenting all the results here because it'll be a very big table, just a representative summary. So we have various covariates here, and we have estimates, point estimates, and 95% confidence intervals from complete cases and multiple imputation respectively. And we can see that the point estimates from both are in the same sort of ballpark figures, which is nice to see because we know complete cases should result in unbiased estimates. So it's good to see multiple imputation isn't too far away from complete cases. But crucially, the 95% confidence intervals were all narrower than the 95% confidence intervals from complete cases. And so even though we're adding in that extra piece of uncertainty through the imputations, because we're not throwing away so much data, we're sort of gaining in terms of our reliability and certainty of inferences. So that was a good finding already to see. Now, obviously, we don't know what the truth is here, right? It's real data. We don't know what the original values of the missing data were, but we'd like to do some simulations just to give us some sort of sense of how the different methods perform. So in order to do that, we subset the data based on the complete case subsample. So we come back to a fully observed data set by focusing on the complete cases. And then we randomly reintroduce missing data back into the data by reintroducing the patterns back consistent with how they appeared in the real data. So the idea is to try and preserve the structure of how the missing data occurred in the original data. So we kind of want it to look sort of similar to try and keep it sort of more sort of representative, if, as much as possible. And then we obtain estimates from using multiple imputation in complete cases applied to the subsample. So we get the estimate from multiple imputation, we get the estimate from the complete cases of the complete case subsample, as it were. Hopefully that makes sense. And compare these to the estimates obtained from this now fully observed complete case data that we're starting from. So that's kind of like the gold standard, and we'd like our estimates to be as close as possible to the estimates from this fully observed complete case data. And then we repeat that process about 100 times to get some sense of stability. So one thing we did is we computed the sum of squares differences from the complete case estimates to the true gold standard estimates, as it were, and averaged those over the 100 replications. And that's like a surrogate measure of MSE, mean squared error, we're calling it. We did the same for multiple imputation and plotted those MSE values for multiple imputation against complete cases with this y equals x line here. So basically a point below this y equals x line means the complete case estimate has a higher MSE than multiple imputation. And we can see that all the points are below the y equals x line. So we have a lower MSE due to the improved reliability, lower variance really with multiple imputation. And we also plotted the average confidence interval lengths, again, from multiple imputation against complete cases with the y equals x line here. And almost all the points were below the y equals x line, indicating complete cases had a larger average confidence interval length than multiple imputation. So again, good encouraging signs for multiple imputation here. The other thing we did briefly is we did a stepwise regression on each of these 100 simulated data sets. On the, we obtained the subset of variables on the complete case data, and then we did multiple imputation on the and then applied and obtained the subset from the multiply imputed data sets, and we obtained the subset on the complete case of the complete cases, and then we just compared those. We wanted to see basically the proportion of correct covariates included, which is of the left figure, and the proportion of covariates that should not be included in the right figure. So again, multiple imputation is on the left, complete cases is on the right. The higher the box plot on the left, the better, and we can see that we did better on the complete cases. We did better than complete cases, and lower is better here in terms of that we shouldn't be including the variables we shouldn't be including in the subset. So again, multiple imputation did better on both. So I will just conclude there. Which, so apologies for the late drama, but we see that there are advantages in using multiple imputation when missingness is missing completely at random, even when there is a large proportion of missing data. And we wanted to think about what other areas this missing by design problem could be an issue. For example, meta-analysis, if we were combining several data sets together. So we thought, well, suppose we combine different clinical trial data sets together, we might end up with this kind of missing by design problem because different data sets have different collection practices. And so that leads to a more general problem where we assume an underlying structure to the missing data, because we're thinking that the data set has some kind of reasons for the, for how the missing data occur in your data set have some kind of relationships. And so the structured missingness is basically something which is a more general problem, and it's going to be quite likely in large complex data sets, particularly when you construct it from different sources. It presents some unique challenges and something that we're actively working on through this partnership. I'm not going to say any more on that though, because I know Chris is going to say more on it now. So I will end there. I'll just say that we have this paper in the Biometrical Journal if anyone wants to read more about it. I'd just like to acknowledge my collaborators at NHS and University of Southampton and the grant that funded that work. So thank you very much.
Thank you so much, Robin. I'm glad you're okay.
That's the first time that's happened.
Yeah, that was really great. Just a reminder to everyone that you can pop your questions in the Slido. I'll repaste the link in the chat. And now we're just going to hand over to Chris before our Q&A session.
Great, thanks, Vicky. So if you could stop sharing, Robin, then I can. Yeah, wonderful. Great. Okay, so yeah, no, thanks, Robin, for that introduction to missing data. As Robin said, we're sort of an area which we've identified, and it's come through from several different angles, is around structured missingness, which is a specific format of missing data, which we believe has got a lot of unanswered questions, actually sort of be quite an evolving research area to move forwards in. So what I was wanting to do today was just give a quick introduction about what is structured missingness, including sort of just another example of where it can arise. Then talk a little bit about structured missingness as an emerging research area, thinking about some sort of the challenges which exist in this area. Again, all open to areas of research we can move on forwards with. And then finally, just talk about characterising structured missingness. So this is sort of one of the areas which we think is, one of the key grand challenges to be addressed, and sort of some initial thoughts we have on looking at that. And before I go any further, I'd just sort of like to acknowledge a whole huge number of people who've already been involved in some discussions around this. So we've got sort of our partners from both the Alan Turing Institute and from Roche who've been involved in discussions as part of the partnership. But as Vicky mentioned, we had a series of workshops at the end of last year where we sort of explored quite a number of the different issues around structured missingness. And this was, really well attended, and some great discussions came from this. So again, I'd just like to thank the participants who took part in that workshop and really sort of helped crystallise some of the thinking we have around this area. So what is structured missingness? Well, in some cases, it's what we sort of see is it's a bit of an inevitable consequences of combining multiple data sets at scale. So as we sort of look towards solving some of the bigger challenges that we have, which we're looking to data to solve, we're going to be start to combine together data sets from different sources in order to just achieve the richness of different variables we have involved, or just the sheer number of patients involved in order to make sort of the types of steps forward we hope to get. And what we sort of see is that however we sort of start to add together data sets, whether it be sort of adding together different modalities of data, for example, genomics and imaging data, we're going to have some patients, there's going to be alignment, we're going to be able to combine this together for some patients, but there's going to be some patients who have one form of data, but not the other form of data, quite like the other way around. And that's going to give rise to some sort of structure within the data. Similarly, if we add together subjects from different data sets together, we can imagine stacking them on top of each other. But there's going to be some variables which may get measured in one data set, some variables which may get measured in the other data set, which also end up with these effects going on. And just to say, this is sort of probably the simplest example of where we get the structured missingness. There's many more subtle effects can also occur. For example, sort of the example that Robin gave in his presentation. So it's really distant coping with any sort of situation where we sort of see this structure of within our missing data, within our data sets. So one of the examples which was strongly motivating from the Roche side, and we get involved with this, was thinking of one of the data sets which we have access to is this Clinico-genomic database. So this is sort of an exciting data source in that it connects together two data sets which are both rich in their own right. So one of these is Flatiron, which is a set of electronic health records which have undergone a great degree of very careful curation in order to turn themselves into what we call research ready or regulatory ready real world data. And this is a combination of both sorts of information about a patient's history through their oncology treatments and the state of their treatments at any time, and also linked to the clinical outcomes which come from those treatments. The other data is from Foundation Medicine. So this is a company which provides comprehensive genomic testing within cancer. You're providing measurements across a whole range of different genes related to oncology. And then what we have this combination of both of these together. So this has now been growing over a number of years to form quite substantial, now in excess of 100,000 patients across all different cancer types, which allows us to link together both the genomic background of the cancer, as well as the patient treatment and the patient outcome from the cancer, which, as you can imagine, is a very powerful tool to be able to use. But within that, we do see a number of different examples of structured missingness occurring within this. So, for example, one of this comes from the block missingness from measuring different genes from different patients. So what happens is that each patient will typically just receive a single test, but there are a variety of different tests which a patient may receive. This can be because the test which a patient may receive is actually targeted towards their needs. So it could be targeted towards how the test will be used. And for example, we have different tests for solid tumours and for hematological tumours, which are most relevant, contain the genes most relevant to those patients. There's also been an evolution of tests over time as well. So what we see is if we go to the right-hand side, this just shows for each of the different columns represents each different type of test which different patients may have received. And the vertical rows represent the genes which were represented within that particular test. And when we actually look at this, if we were only to take complete cases analysis, which is those genes which are measured in every single data set or every single test, we're only looking at 30 different genes. But clearly there's a whole range of additional information within the overall data set which we want to use. It's much richer than that. So what we have here is a situation where the genes are block missing by the test type that a patient received. And there could be different reasons behind the particular choice of test which a patient did receive. But that's not the only source of structure missingness within the CGDP. Because the database is actually pan-tumor, so it's going across all different types of cancers which are collected within the data sets, then what we also see is an effect where different cancer types often collect specific information relevant to that particular cancer type. So for an example, a prostate cancer type has specific measurements of such as a Gleason score or PSA, which would never be collected for other cancer types. And if you think that typically a female patient wouldn't have no meaning for that patient at all whatsoever. So yeah, it has a very different type of missingness within there. So there's another block missing which is occurring here by the cancer type. A lot of measurements don't get measured for situations where it's not relevant for that particular cancer which that patient has. So in all, what's this which makes structured missingness something worth considering and spending time on? So what we sort of see is if we're combining data sets at scale, it's probably going to be quite inevitable. In fact, we look around and we see it sort of quite ubiquitous in any of these very large scale databases which we're increasingly generating in order to mine for data healthcare insights. It's also true that many analytical and especially machine learning methodologies work on having complete data available. So it does require us to do something with that data in order to just be able to use the standard methodologies which we have. But it also has its additional features above the standard, just what we may think of unstructured missing data. This may be additional challenges just due to the shape of the missingness data, which may be very sparse in some cases. Can make the difficult data much harder to use. But it's probably also additional opportunities by taking advantage of the structure that we know to be in the data that could give us some more insights and give us some more power of what we're able to do with the analysis. As with all missing data, there's also the chance that some of this data may contain information in its own right. It may be informative, we may be able to use the fact that the information is missing for a certain patient at that time, may tell us something about that patient at that particular time course, which we're going to use to inform our analysis. And another factor which is also worth considering is that the missingness may also highlight limitations of the data. For example, underrepresentation of certain groups within our data sets. Again, this can occur at our whole data set as well, but it can also occur much more subtly within data sets. For example, it may be that certain tests with genomic tests are much less frequently available for certain socioeconomic groups, for example. So hopefully now, if we've sort of established that we think that structured missingness is something important and worth considering, we just sort of wanted to lay out some of the ideas of some of the big challenges or big questions which we sort of see within this area, which we'd sort of like to look at in some ways. So one area is actually really defining, characterising what structured missingness is. I've sort of given an overview of this here, which is a little bit hand-wavy, but probably in order to make real progress with this, we probably do need quite a rigorous definition of this. And what's also clear as well is that it can be characterised, it can appear in many different forms. So we probably need to have a real characterisation of it, a way of describing what's going on in structured missingness in order to make some real rigorous progress in the ways we can be addressing it moving forwards. But on top of that, then being able to explore structured missingness, to be able to understand the pictures of what we're seeing in the structured missingness, and to be able to identify it with data sets is going to be really important. And you can imagine there's a lot of things there. There's a natural visualization which will help us to understand this. There's probably geometrical representations which will help us to understand what's going on within these data sets. As with all analyses, the way in which we address the structured missingness, it may depend the optimal ways of doing it. So what we finally want to do is the final downstream analysis. And for different applications, it may be different approaches for use to addressing the structured missingness initially may be optimal to be performing. So you can think that actually there's maybe different solutions for sort of some of the major areas which we'd use this for which may be for prediction, for example, it may be around inference and estimation as another typical class of problems which we may be trying to address. Causality is something which we sort of see as a thread which is running through the whole questions around structured missingness. We can see this may be actually something very important in understanding this structured missingness to start with, the causality of understanding why structured missingness arrives in some situations. And yeah, that may help us to understand what's causing it, which in other words gives us some ideas and directions in what to do in order to address it. But also many of the analyses downstream of that, prediction and inference and estimation, will often be phrased in a causality type of framework. So it sort of makes the question, is there some overall causality, causal inference type approach you can take, which will actually naturally incorporate structured missingness within it? As Robin already mentioned, imputation is a very common tool in order to address missing data. And it's sort of a question then about how does this apply to structured missingness? Does the same sort of approaches as with standard missing data, for example, using techniques as mice, seem to make sense? Or are there more kind of subtle mechanisms which can be actually used, which will actually take advantage of the structure we've got in this data and give either more powerful or more robust imputations and therefore more reliable downstream predictions from our data than we might otherwise get. As a statistician, one of the things I'm always thinking about is the design. So actually, if we've got a problem, could we have actually avoided that problem in the first place by designing our studies, designing our data sets better in order to circumvent that? Within sort of structured missingness, one of the questions is thinking about sort of the fairness of our data. If we know that our data is going to be reused in some way, it may be combined with other data sets, are there steps we could be taking in order to facilitate that, to kind of minimize the amount of missing data we get moving forwards? Just thinking about implementing standards and issues like that. As with all of these, any sort of methods, we're interested, we can imagine we'll have a plethora of different methods, a plethora of different approaches for dealing with structured missingness. We really want to be understanding what's the optimal case to be using in different scenarios. And so we really need to have some ideas around benchmarking and evaluation. I think one of the challenges here for structured missingness is there's probably an extra complications in a number of different ways data can appear. A number of ways that we can get structured missingness. So there's sort of the number of different things which has to be looked at can end up being rather complex. So we need to think about a structured framework or structured principled approach in order to evaluate the methods for evaluating structured missingness. And a final consideration, but really critically important, is that of the ethical implications of this. Really sort of thinking about if we've got structured missingness within our data, which may have some link, it may be that protected groups, for example, are much more likely to have missing data because of their protected nature. They're not wanting to disclose information. How can we build that into our analyses to ensure we have something which is really fair and equitable in the conclusions that we've got and can treat all groups equally? So just sort of briefly finish off, what I was wanting to do was just sort of talk through some of our initial thinking around characterizing structured missingness. And this is sort of recognizing the idea of some of the original ideas around MAR, MCAR, MNAR that Robin described earlier. There's kind of an additional layers of complication which go on when we're dealing with these structured missingness, which may not be relevant, may not mean those approaches for characterizing it aren't complete. Don't give us enough opportunity to really describe what's going on here. I'll just sort of describe it using this picture here, which we've used to sketch out some of the different dimensions of how things can change. And there are really two key dimensions on this. So on the vertical axis, what we've got is the relationship of the missingness to the values in a data. So this may be situations where a patient who is particularly sick may have particularly high values in a situation. For some reasons are, for example, either much more likely or much less likely to have missing data in that case. It may be because of their disease, they're unlikely to undergo an invasive diagnostic technique. Or it might be only those patients who are more seriously ill who actually will undergo the particular diagnostic test. And then we can split that up. We can sort of see that we may have things which are generally occurring at random. We may have things which are related to where the missingness is determined by other variables in the data set, not the one variables which may be missing or not, but other variables. Or it may be related to the values of the variables which are potentially missing. And then in all of these dimensions, we've got sort of something where it may be a deterministic type approach. So for example, in Robin's case, it's a very clear thing that something happened in the past which was different to something which happened to the later patients. So given the date of diagnosis, there's a very clear yes, no. Or it might be more of a probabilistic type measurement. So it might be just those patients who are more seriously ill are less likely to get a test, but it's not a deterministic clear-cut measure. On the horizontal axis, what we've got is the data which is related to the missingness in other data sets. So we may have situations where it's unstructured, but we also may have situations where there's relationships between missing variables. So basically, if you're in a situation where one variable is missing, you also know that that variable is either another variable is more likely to be missing, or definitely will be missing. And this is what we characterize as strong and weak, as being a deterministic relationship, it will be missing, or probabilistic relationship, which is just more increased likelihood to be missing. And then on top of this hot structure here, we've got another dimension, which is whether the missing value, which we don't see, actually exists or not. So this is a sort of case, for example, if we're looking at the prostate measurements, it may be within a male patient, it just wasn't measured for some reason, the PSA test, but that patient does have a test result attached to them. Or for a female patient, that is a sort of meaningless value, so that value doesn't really exist. And that can be another useful determination to make. So Within this, what we can do is we could then start to characterize a number of different measurements, a number of different structures within this type of data sets. And this is where the sort of the causal relationships can start to becoming useful. So for example, if we look at the left-hand graph on this picture here, what we've represented here is the blue represents the data values for each individual variable, and the red is an indicator variable about whether that data is missing or not. And so what we've got is a situation here where if you've missed one data set, one variable, then you also miss all subsequent variables for any particular patient. And so what that sort of is setting up this strong structure, strong sequential structure within the data set. But it's missing at random in a situation it doesn't relate to the values of any of the data points. In contrast here, we've got another situation where it's actually missing based upon the value of one of the value points there. So the causal relationship goes from the blue value in the second column to all the indicator variables over on the third, fourth, and fifth variables. And there's that relationship that there's consistent values. So whenever one of the variables is missing, the whole situation is missing. So for example, this may occur in a situation where if one variable is just measuring the severity of a disease, and if that's above a threshold, that triggers a situation where the patient does not receive any invasive test. And so it is missing across that whole set of variables moving forwards. And as you can imagine from the previous diagrams, there's a whole range of different types of situations and scenarios which get covered within this whole structured missing situation. So where are we hoping to go next with structured missingness? So we obviously think this is something important and sort of valuable that we want to continue exploring within our relationship. As Vicky mentioned, we're going to be sponsoring some number of research projects in this area. These are still going through a contracting phase, so I can't talk too much more about them at the moment, but we'll certainly be publicising them when they become available. We're looking at the next few months to sort of start to submit a couple of publications on this area. One of sort of the grand challenges, the big questions in this area, and another sort of describing our thinking around characterising structured missingness. And then maybe most importantly of all, what we're hoping to do is sort of continuing to build in a community around missing data in general, I think, but structured missingness in particular. And again, just to sort of give a shout out, as Vicky mentioned at the beginning, of our various Slack channels, ways of communicating together, and that we may sort of hold future events in here. So yeah, just to keep aware of what's going on in the partnership. So thank you very much for listening. And I think if I hand over to Vicky, we've got an opportunity for Q&A.
Yeah, thank you so much, Chris, and thank you, Robin. So we've just got around 7 minutes for some kind of Q&A. So there's a Slido link in the chat if you'd like to put some in there, or you're also welcome, if you click on the reactions bar in the bottom bar, you can raise your hand and you're also welcome to ask a question directly. But just bear in mind, you will be on the recording if you do that, and you can submit anonymously on Slido if that suits you better. So the first question, I'll get us started on Slido, is there a limit to the number of missing values in the data set must be before multiple imputation is not effective? So I don't know if either of you want to take that one.
Well, I'm happy to start. No, I mean, I mean, of course, yes. I mean, the more of the missing data that's there, the less, well, I wouldn't say effective, but the greater the uncertainty in your inferences. So I suppose I don't really have a very cut and fast answer here. Just a few caveats. Firstly, it's not always the amount of data that's missing; it's the amount of information that's missing. So so sometimes you might have a lot of data missing, but you might have a lot of information to get some good sort of to build your imputation model on, in which case it may not be as severe as you might think. And conversely, you might not have a lot of missing data, but you might have very little information to build your imputation for that part of the data on, which kind of ties into some sort of structured missingness type problems as well, I guess, depending on how your data set, how your missing data sort of appears in your data. So it's more around the missing information, and there are sort of measures of missing information in the literature that are also relevant, that might be more appropriate than simply the pure number of missing data. And the other thing is, the good thing about multiple imputation, as opposed to maybe some other methods, is you can kind of see that coming through in your inferences. So because you're doing this multiple times and you're getting these kind of sort of uncertainty estimates of your, due to the missing data, so your sort of confidence intervals will get wider as you need to do, say, more imputation, or you've got more sort of missing data. So so it's more about sort of being able to assess that and make a subjective assessment of, well, no, my intervals are way too wide, I shouldn't really be be drawing too many conclusions with that. So it's more sort of giving a tool to decide, is this reasonable or not.
Thanks, Robin. Anything to add, Chris?
No, I think that's very clear. I think it's it's not unfortunately it's not one of these with a very clear cut cut off answer. It's going to very much depend on your data set and the relationships within it. Yeah.
So the next question with the most votes is, how can we impute text valued fields that have missing text? Which I can imagine is very challenging. I don't know if either of you have an answer on that one.
I'm not sure if a Roche advanced analytics group have got. I think I think it's a really great question. I have not done anything on this myself, so what I'm saying could be very nonsensical, but I know some people are doing stuff on NLP and things like that, machine learning type processes. So multiple imputation started in a very classic survey actually driven world, where things were nice and clean and we're just dealing with sort of numerical values or categorical values. But obviously, when you come to more challenging things, machine learning is, of course, now methods are becoming very appealing and are sort of synergizing with some of the traditional statistical procedures. And so my hunch would be to do something more quite sophisticated using some sort of machine learning type methods. Kind of if you were predicting, you could see ties with prediction there as well. In terms of the theory and the statistical theory, we're not necessarily stepping outside of the domain where the classical theory was developed, but that's not necessarily should be a limitation. It's because a problem might require that. So, but I would suspect you would need some quite clever machine learning approaches to deal with some of those challenges. Yeah.
I think it's, again, I'd sort of encourage you to think about what's happening next and what the whole route you're taking downstream. So it's how you're going to incorporate and analyze those text fields and actually incorporate it into that bigger analysis. So I could imagine at the very simple level, you may be just turning those text fields into like indicator variables. So maybe picking out a few keywords and yes, no, does someone talk about this topic or this topic or this topic? And you can imagine then if you've taken that to the next stage, attention numeric variable, then you could probably impute onto those numerical values in the same way as if it was directly measured numerical value. If you're taking a much richer view, sort of looking at some of the advanced NLP BERT type analyses, then it gets much more complex.
Great, thank you. I'm just gonna, I think, squeeze in time for one more. Again, on the kind of imputation lines, I know kind of mice was mentioned a couple of times by both of you. So someone's asked, what are the limitations of mice for data imputation?
I've used it a bit, so happy to say a little bit about it. It's an evolving package as well. Basically, the spirit of mice is you've got a data set with, say, I don't know, 10 variables, and you treat each variable on its own, one at a time, and then you just you basically condition on all the other variables, typically for a regression model, and then you impute. But so its strength as well as its weakness is that it's very flexible, and so it's not tied to a particular theoretical basis. There are people that have developed some theory around it, but the original approach didn't claim to have any theoretical kind of principles behind it, but it worked, and it can be done. So for example, you can choose the kind of model you want to use. If you've got a continuous variable, you might want to use a normal regression to impute from. If it's categorical binary, you might want to use logistic or probit. So it's very flexible, and you can do what you want in some senses with it as an approach. Of course, the theory around it sometimes is there and sometimes isn't. In terms of a package, I think the question was around a package. Again, it depends on what software package, what sort of software you're using. I'm familiar with it in R. And again, it has add-ons and it continually gets developed. You can do, it works fine for a kind of rectangular data set where you've got sort of, a fixed number of rows, fixed number of columns, and it can handle sort of things like continuous categorical variables and so forth. And like Chris said, if you were dealing with sort of text data, if it was viewed as a category and so forth, it would also potentially be able to handle those as well.
Perfect. Sorry, I'm going to cut you off, Robin, just because we're, yeah. I just want to thank everyone for coming, and Robin, for Chris, for some fantastic talks. They're both available on the Slack channel. So sorry we didn't have more time for questions, but please pop any more questions in the Slack channel and they'll both be able to answer them there. And also we're having our next event in May on predictive modeling in healthcare. Again, I've popped the link in the chat, so I do hope you'll be able to join us then. And we will be sending the recording of this event around afterwards, as well as a feedback form. As we mentioned, this is our first event, so it'll be really useful to kind of have your feedback on how it went. And thank you all for joining. Hopefully see you next month.
Thank you, Vicky.